for a second. I am beyond thrilled to introduce to you Dr. Bala. He and I worked together for 20 years at Xerox, and he was a mentor to me that whole time. We have, I think, a dozen patents in common, although Raja has 170 patents, which is a few more than I have, so that's very impressive. He's a principal scientist and leads the computer vision group at Palo Alto Research Corp, which is still a part of Xerox?
Yes.
And I'm sure you've heard of Park Research Center, one of the premier research centers in the US. His interests are sort of the intersection of digital imaging, computer vision, and machine learning. So hopefully this will be of interest to you all. He was a principal engineer at Samsung Research, where he developed innovative computational imaging technologies for Samsung's high-end smartphones. And senior member of IEEE, and has over 100 publications. So I hope you enjoy his presentation.
Well, thank you very much, Karen. Thank you and Guyo for inviting me to the series. It's really a pleasure to be back at RIT. The premise for my talk today is that I think, as we all know, we are well into the era of big data. And along with big data and powerful computers comes the era of deep learning, which I think, as many of us know, has defined the forefront state of the art for many problems in computer vision, natural language processing, speech recognition. People are using deep learning for even fundamental problems in science, such as discovery of molecular structures and drug discovery and so on. So deep learning is all the rage. But one of the challenges with deep learning is that you've got these gigantic deep neural networks, which have millions, if not billions, of parameters. They're very complex. And so in order to train these deep networks, you need lots and lots of data if you want to avoid overfitting. And not all applications afford us the luxury of big data. In fact, if you look at companies like Google and Facebook, whose whole business is around big data, they are indeed at the forefront of deep learning and technologies around deep learning. But not a lot of applications give us that luxury. So how do we deal with this problem? So that's really what this talk is about, addressing the small data challenge. So as I just said, deep learning is great because it provides these really rich generalizable models, but require a lot of training. And that's often not practical for many scenarios. A good example would be in medical imaging, right? One can't imagine conjuring up a billion images, MRI images of some organ that easily, much less, even if you could get the images, annotating the images, because deep learning, supervised deep learning, requires images or video and associated ground truth or annotations, and makes associations between the two in order to predict those ground truth annotations in new images. So in a niche application like medical imaging, it's not only hard enough to acquire data, it's hard to annotate data. So how do you train a deep visual? How do you leverage the benefits of deep learning, the high modeling capacity of deep learning, with sparse data sets? So this is not a new problem that the community, AI community in general, and the computer vision community specifically is sort of wrestling with this problem, and people have a number of different approaches that they bring to this problem. One of the popular ones is data augmentation and data synthesis, which is that if I've got a limited number of real images, can I generate synthetic or fake images to augment real images? In image synthesis, again, there are a couple of flavors. Some researchers use first principles modeling using, for example, computer graphics rendering techniques to build models of scenes. At Park, we use game engines like Unity to generate scenes of video and sort of drive through and fly through videos to train some of our computer vision algorithms. Good example here is at RIT, there's the DIRSIG system, which simulates for remote sensing applications. It has realistic models of the terrain, atmospheric effects, and sensors, and so on. So that's a good way to generate synthetic data, provided that the synthesis can capture the variations and the noise and disturbances of the real world. Another flavor of image synthesis uses statistical techniques to generate images. So, and again, I think there's a diverse set of audience here, so some of this may be well known to you, some of this may be new to others of you, so bear with me at either end. So on the statistical side, the same deep neural networks which were originally used to take in images and do some sort of prediction or detection can also be flipped around to synthesize images. And today, there are a lot of very advanced techniques to produce very, very realistic images with techniques called generative adversarial networks, or GANs. And I'll talk a little bit more about this family of techniques. Another family of techniques takes some base network that has been trained on some gigantic data set like ImageNet and uses it as a starting point to fine-tune your deep learning for your particular problem. And that can work okay as long as your task is closely related to the pre-trained task. If you have a big mismatch, you might run into problems. Sort of building upon that with more sophistication, you've got a variety of techniques around domain adaptation or transfer learning, which takes the knowledge and models in one domain and transfers it with some formalism into another domain. Another sort of class of techniques is called semi-supervised, which means you've got a whole bunch of data that's not annotated, and you've got some data that is annotated, and can you sort of mix them in and use sort of the sparse annotations to inform you about the bigger data set. So these are sort of flavors of techniques people are looking at. So at Park, so this graphic summarizes the talk, and I think it's the one that went along with my abstract. So again, you've got standard deep learning. Sometimes you've got to deal with small data. So we have a number of flavors of techniques we pursue to attack the small data problem, and some of them relate to some of the well-known techniques that I talked about before, and some are unique, at least in our view. So I'll walk through these for the rest of the talk. So one flavor of techniques we're looking at is bringing intelligence into the network itself. Right? The network requires a lot of data, but if you can provide it with some prior knowledge or a hint about the domain you're looking at, the image, the nature of the images that the network is analyzing in terms of some sort of tractable prior, then the network doesn't depend as much on the data. So that's sort of one flavor of techniques called regularized deep learning. Another flavor of techniques puts intelligence into the data. So if you have a scenario where you have, say, billions of images from a public data set, but they're not annotated, and you've only got a small number of images that are annotated, can you do some sort of label prediction or label propagation from the small set to the big set? So that's, I'll talk to you about some unique approaches we're adopting there. These two techniques are fully automated. They're using the machine to bring intelligence into the network or the data. The other two bubbles are sort of interactive human-in-the-loop approaches. We have a unique way of annotating objects in 3D using augmented reality, wearing an augmented reality device and leveraging the 3D sensors and the 3D capture capabilities of AR to annotate objects in 2D. I'll talk about that. And then finally, this last thread, which is another principle that we adopt in our research, is that whether you have small data or big data, I think it's important to have good data. So if at all in your application you've got control on the image capture and can control the parameters of the image capture, then by all means one should co-optimize the capture with the analysis. This is sort of a systems view that we also adopt. I'll give you an example of one application where we actually use computer vision to filter out bad images before we run it into the computer vision task. So in the hour, I'll sort of go through these 4 or 5 threads. And since we only have a short time, my idea is to sort of describe them at a high level and sort of convey the intuition. I won't go into a lot of the gory mathematics or details, but I'm happy to answer questions. By the way, I'm happy to keep this interactive. Please ask questions along the way. Also happy to sort of chat about any of this stuff afterwards. I also have references to many of these techniques in the slides as well. With that, we'll jump into the first flavor of techniques, domain-specific regularization. So again, the idea is that if you know something about the domain you're working with, can you formally incorporate that into the network? So we ask ourselves questions like, how are objects formed in nature? How are images formed? What is the geometry behind the objects, the images? Is there a model for how the light interacts with the object? Is there a model for the camera we can incorporate? Because at the end of the day, computer vision algorithms are not looking at random patterns, right? They're looking at pixels that are arising from some natural phenomena. Can we model that natural phenomena formally into the deep learning pipeline. Similarly, what are the characteristics of scenes in nature? Many of us know that there's a sort of a low-dimensional manifold on which many images lie. They're not just random patterns. Can we discover that manifold and use that to constrain the deep learning pipeline? So if we can do that, we want to incorporate this sort of information into the network in a couple of different ways. We can use priors in the loss function of the network, or we can impose some structure into the filters of the network itself. And I'll give you a couple of examples of how one can do that. If we can do this well, fundamentally we have a principled way of addressing the small data problem, because you depend less on data and more on some sort of structure of the data. We also expect, and we've shown this with one application at least, that if you build some intelligent domain-specific priors into your network, it also generalizes better. It is not optimized only to fit one data set. It can easily generalize it to other data sets. Also, domain-specific priors bring some level of interpretability to your network, because you're designing your network with some knowledge infused into it. It's not as black box as purely data-driven approaches are. So this is all very well, nice philosophical general statements to sort of demonstrate this idea of domain-specific priors. We chose to attack a specific problem as an example, and the problem we chose was curvilinear object segmentation in images, which is the task of finding thin, fine, curvy structures in images. And part of the reason we took this particular problem amongst a myriad other problems is because, first of all, in many of the applications in this problem, the data sets are actually quite limited. And it turns out that curvilinear object segmentation is useful in many different applications. I have listed 4 here. Looking at blood vessels in the human body, in the retina, are curvilinear. Looking for wrinkles on faces, looking for roads in aerial images, looking for cracks and defects in machine parts. And it turns out that Park has a number of commercial projects in some of these areas, so it drove us to explore this general problem, right? So curvilinear segmentation is the general statement. Again, to practice and to demonstrate, we chose one particular problem, and we've actually looked at its generalization to others, but the problem we looked at was retinal image segmentation. So we'll take a couple of minutes understanding this problem, right? So what is retinal image segmentation? It turns out that if you can take this image on the left, which is a retinal scan taken from a standard RGB fundus camera, and can extract the blood vessels going through the retina, giving you a map as shown on the right, there turns out to be a pretty useful diagnostic aid for clinicians. So clinicians can detect from these blood vessel maps early signs of diabetic retinopathy, glaucoma disease, and so on. Especially with the thin vessels, abnormalities are early indicators of disease. So if you can go from the image on the left with all this background noise and lack of contrast to a map on the right, it's very useful. So that's the motivation. However, this is quite a tough problem because the images are of low contrast. As you can see, the vessels are widely varying in their geometry and their thickness, and there's lots of other interfering structures that get in the way. So how do we approach this? We did a big literature survey and found that, as with many other tasks, deep learning has defined the state of the art. The best segmentations are coming from deep learning. So we said, okay, we've got deep learning. What can we do with it? There's not a lot of data sets. The standard data sets people use to train deep networks, drive and stare, have 40 images and 20 images respectively. Where does that contrast with billion, right? So you've really got a small number of data sets. You can play tricks by taking patches and augmenting them, but still, small data problem. So very briefly, the approach we take is the network architecture itself is actually quite simple. So we've got an original image. I just showed it in grayscale, with the image on the image on the left. It goes through a deep network and comes out to form a segmentation map. We parse the network into 2 steps. There's a representation layer and a task layer. The representation layer takes the original image and generates an intermediate representation that you can think of as a first guess at extracting these curvilinear structures. And the task network then takes that representation layer and refines it into the final map. I'll talk about this in a bit more detail. The network loss is, how many people are familiar with deep learning? Number of hands, okay. So I'll try to keep this as intuitive as possible. So this is a typical deep network architecture. You've got a cascade of different types of layers. Some are convolutional, some are fully connected. In this case, you have primarily convolutional layers because you have an image coming in, an image coming out. So the network loss, we have a network, it has lots of parameters. Each of these slabs has tons of parameters in it. They're filter parameters which we have to optimize in order to get this answer from this image. And the way we do it is we give it lots of examples of inputs and outputs, that is input images and ground truth Bessel maps. And you train the network to say, hey network, I want you to produce an output that's as close to the truth as possible. So we optimize an objective function. The first term is what we call the data term. We want the predicted map to be as similar as possible to the true map, which has been provided by doctors labeling these images. So that's the standard network data term. We then introduce a couple of losses. So this is where we bring our sort of novelty into this, which is a way of introducing domain knowledge. The first constraint, it says that blood vessels are curvilinear. They have a lot of orientation. They have strong orientation properties. So we give the network a hint to say, you need to be looking out for strong, noodly structures with strong orientation. That's a hint we give it, right? That you don't need billions of examples. I'm just telling you that vessels are going to look like this. The second constraint says there's also a specific type of noise that one sees in retinal images. We'll give you a hint at what that noise looks like. So hey, when you see that noise, please suppress your response to that. So intuitively, that's the idea behind this. So I will click a little bit on each of these boxes and give you a feel for what's going on. First, the representation layer. So as I mentioned, we have two terms here, orientation and noise. These are the two domain-specific constraints. So, fine, okay. The orientation, I'm going to kind of go through this quickly. What we do is, along with the retinal images that come in, we hand design a set of patterns and run them through the network as well, and force the network to respond in specific ways to these patterns. You see, these are sort of simple simulations of curvilinear vessels that we hand design. What we say is, if you notice, there's a set of filters here at different responses. For every filter, every pattern, I should say, the pattern at the bottom is orthogonal to it, right? So you can see that the patches on the lower row are orthogonal to the patches in the upper row. So we design our loss function in such a way, I'll just sort of go through this, that this is a term we're minimizing. It's a difference of two terms. The first is the filtered response to the top row, and that's the second term, sorry. And the first term is the filtered response to the bottom row. So all this is saying is, when I do this minimization, I'm going to generate filters in my network that get really excited when they see these patterns, but are suppressed when they see these patterns. It's just a way to make filters more sensitive to orientation, okay? When we do that, and so that's really, again, the first term of the optimization. So when we do that, what's interesting is you can visualize the filters that come out of the network. You let the network train, right? Large number of iterations. When it's done, you plot what the filters of the network look like. If you have no orientation diversity, you just let the network train on retinal vessels, you get structures that look like this. But if you put in the orientation diversity, you can see that you're encouraging the network to, the filters of the network to be sort of sensitive to curvilinear structures. Yes?
So may you go back to the previous slide?
Sure.
So that now those filters are limited. I mean, you only have there like 6 of them. So.
Oh, yeah, that is just for illustration. We have a bank of about 30 filters.
Oh, like 30 filters.
Yeah,
okay.
yeah.
So
and that's also hyperparameter. We pick how many filters we want. Yeah.
So does it change if you increase the number, I guess? It changes if you increase the numbers of filters, I guess.
That does what? So the network's performance does have some dependence on the number of filters. It's a hyperparameter. So we play with different numbers, and we ended up with somewhere between 25 and 30. But it's a function of, so retinal vessels can orient themselves in arbitrary orientations. Yeah. So yeah, so you have to trade it off. You want it to be able to distinguish orientation, but at the same time you want good filter response, so you have to trade those off. So it's a hyperparameter, it's a heuristic parameter we play with. So this is just to say that, okay, the filters are now paying attention to blood vessel-like structures. Quick demonstration of what happens if we, this is the output of the network with the diversity constraint. Just to quickly explain the color code. White means my prediction agrees with the truth, so we want a lot of white. Red means that the network predicts a vessel where there really isn't one, that's a false positive, and green is the opposite, where we miss the blood vessel. So we hallucinate a lot and create a lot of vessels and miss some without the orientation constraint, and generally see more white when we put in a constraint in this numbers to show that you get better performance. We also extend this to multiple scales. One of the challenges I mentioned with retinal vessels is that some are very, very thin, some are very thick, so you want your network to handle multiple spatial scales. So we have a simple adaptation to that I won't get into. The next constraint is noise suppression, and the way we do that is that we do it in two passes. We run the network through first without the noise constraint and see where, the places where it makes mistakes. So if you look at these retinal images, you find these turn out to be false positives. I don't know if you can see the circles marked in dark red, but here are examples where they masquerade as vessels, but they really aren't vessels. So we give it to the network and say, hey, network, when you see these sorts of patterns, please suppress them. So there's a term that suppresses noise, which in the interest of time, I won't get into, but that forms the third term of the network. But more importantly, the result, without noise suppression, built in as a constraint into the network, we get an image like this with a lot of false positives. But when we suppress noise, we get a much cleaner output again. And it turns out that this is very important because noise is confusing to clinicians when they're trying to do their diagnostics, right? So that's the first part of the network. The second part is a standard network called residual net, or ResNet, which is good for sort of refining a particular signal. We already have a good guess here. We're trying to refine the guess. So ResNet turns out to be a good architecture. Won't get into that. But so that's the whole idea. We put it all together. We've got three terms, and we co-optimize to bring these domain constraints into the network. Here's a couple of examples of, we did, just had journal papers just came out in transactions and image processing, so we have lots and lots of results and gory details here, but you could compare it with many techniques. But here are two state-of-the-art deep learning techniques, and here's ours. And again, you want to see more white, and sort of both the red and green are mistakes, and generally it's a pretty competitive method. Here's one of the results that excites me the most. We did an analysis of what happens when you starve the network of training data. So we start off with 100% training, you get a certain performance, and then you gradually give it, I think we tried a couple of data points, 40% and 10% of training, and we're measuring accuracy of the network. Higher is better. The blue curve is ours, and these are some of the top competing methods. And because you bring in some domain knowledge, the network is robust when you starve it of data. It still does pretty well when you have only 10% of the training data, right? So I think that's one of the promises of sort of domain-specific regularization. So that was one example of how you can bring in domain constraints under low data. So sticking to the same bubble of domain-specific, another problem we've looked at is, so the retinal image was one of analysis. We've also looked at image synthesis. As I mentioned, image synthesis is a good way to deal with small data, right? If we can generate images artificially, then you sort of end up, that's a way to sort of bolster your data set. So we have looked at generative adversarial network. There's a very rich body of literature here. How many folks are familiar with GANs? Okay, enough hands that I can spend a couple of minutes on this idea. I'm going to go through it quickly. So first, lightning tutorial on GAN. A GAN is basically a neural network that can produce very realistic looking images. So a 1,000-foot view, right? And the way a GAN is architected is it's actually a pair of networks. There is a generator and a discriminator. The generator takes a latent code or noise and generates some realistic looking image. And this is a deep neural network. The discriminator distinguishes whether the image that is coming to it is a fake one from the generator or a real one from a training data set. So it turns out that these two are set off to play and compete with each other in a game, so that by the end of this game, when it converges, the generator gets really good at producing images that are close to the training set, and the discriminator then has a pretty hard time telling between what's coming out of the generator and what's coming from the training set, right? This is a brainchild at the end. Goodfellow and et al. From 2014. It has spurred a very rich direction of work. with this sort of basic idea. So this is the very basic GAN from 2014, right? Now, okay, there's been tons of improvements. Today you can get some very realistic images from state-of-the-art GANs. So, okay, so I can produce 1 billion images with this network, but what good is 1 billion images if I don't have annotations with them, right? So I actually want to solve the small data problem. I want to get big data with annotations. Well, there's a variant of it, which is called conditional GAN or supervised GAN, where, again, high level, you give it images and some tags, and it learns to produce images with tags, right? And the discriminator has to tell whether not only is the image real or fake, but does it actually have the right attribute that you want, okay? So this is a whole family of techniques that can produce labeled images. But there's a bit of a catch-22 here. In order to train the image to get annotations, you need to give it images with annotations. Okay, so sometimes you don't even have, this is a problem, right? Annotated data is a problem. So what we look at is sort of an intermediate setting, and there's others who've looked at this as well, where you have lots of unlabeled images available to you and only a few that are labeled. So now I'm giving sort of interesting examples like glasses and bangs and pointy nose here. But one of the applications that motivated us was we do a lot of work with Procter & Gamble, which is a health and beauty company. And they wanted us to build AI, deep learning algorithms to predict skin conditions. And I'll touch on this again a little bit later. Well, it turns out we don't have billions of images annotated with skin condition, but you can get a lot of images on the web, which are just plain images. They gave us a handful, 100 of images with skin condition. So now you have a good example of a setting where the labeling is expensive, it requires domain expertise. We only get a few label samples, but we can go online and get bunches of face images. Can we do something with this combination? To generate a large corpus of images with labels. It turns out you can, so this is an approach that we took that I'm going to just convey the intuition on, right? So again, generator to generate images, and you've got a discriminator, but in this case, we build a pair of discriminators that police this generator. One only looks to see if the image is real or fake and doesn't require any tags or labels. So this can work on this large image set to build a model for what face images are in general. In this case, I'm looking at face images. And then the second discriminator looks for the attributes, right? Is there dark hair, are there bangs, are there glasses? Now, both are deep networks, both require a lot of data. But the trick here is that the second network doesn't have a lot of data, you don't have a lot of labels. We use the first network to regularize. We give it a prior that says, this is what faces look like. And once you have a prior that says what faces look like, it turns out you don't need so much data with the labels to do an accurate job of predicting labels. So intuition is we're using unlabeled data to provide a sort of a prior, a regularizer for labeled data. Right? Again, the power of regularization, the power of knowing something about what face patterns look like. You don't need labels for that. Okay? So that gives us this sort of powerful way of dealing with this particular scenario. I'll just go through another, just for interest of time, an example of the result we get. Here we trained on digits, and this is the output of images synthesized by our system versus some competing methods. The first two rows are what you get from full supervision if all the images were labeled. So this is a very expensive process. And the next two rows are competing methods to ours, where you don't have a lot of labels. And you see with some of these techniques, when you don't have a lot of labels, the digits get reversed. What was supposed to be a 2 doesn't quite look like a 2. And here, this is a Q, it's not quite there. Whereas when we synthesize, generally we preserve identity. And we did an interesting experiment to show that when you train an OCR system on our generated images, we get like 5% error rate, which is one of the state-of-the-art results. Whereas if you just train on a small number of data, then you get 40%. So again, using intelligent ways to synthesize images in order to train computer vision systems. Apologize if that was fast, but I'm just trying to give you a flavor for, so far it was introducing intelligence into networks to deal with small data. The second family of techniques looks at the data itself. Again, you have lots of raw data with no annotations. Can I find a way to pseudo-annotate raw data? So that's the second family of techniques that we're looking at. The approach is what we're calling ensemble-based learning of labels. So again, the setting is, I have a whole bunch of unlabeled data. I've got big data, but it's not labeled. I've only got a small budget or a small number of images that are human labeled. Or alternatively, I can say I only have a limited budget by way of dollar cost and time for labeling. Let's say I have 1 million images of faces, and somebody tells me I only have the budget and time to label 100 of them. Which 100 of them would you label of the million so that you can do something interesting? So that's the setting for this problem. How can you then auto-generate labels for the remaining data sets? The key intuition that we use here is that we are now in the 7th year of deep learning, and there's a gazillion models out there that people have built that are very accurate for all kinds of tasks. So why not go into this world of models and look for a few that are close to the problem at hand? Not one. If it was just one, it's the trivial pre-training, but look at a few and learn from an ensemble, discover some structure in your raw data by processing it through these ensembles of models and using that to generate labels. So how do we do that? By the way, this is very new work in progress, so I'll just describe it at high level. I don't have a lot of results, but it seems to be quite promising. So the basic idea is I've got a gigantic corpus of unlabeled data, right? I run it through a bunch of models, and there's a principled way by which you can select models which are closely related to your task. You do things like label matching and things like that. And then when you run the unlabeled data through each of these models, you don't extract the output of a deep learning, you don't extract class labels. You take some intermediate representation from the network that it has learned. We call that an embedding. An embedding is nothing but sort of a vector in high dimensional space. We extract embeddings from each of these models. We look for structure in these embeddings, and then we do some superclustering to look for strong clusters across the embeddings. So the intuition here is that maybe this model was used to distinguish dogs from cats, this one mammals from fish, this might be a different computer vision task. So these are all trained differently. These the input data is processed through each of these models, and what that gives me is different perspectives of the same input data. I have different ways of representing the same input data. And I look to see if there are any groupings that survive across all these models. And if they survive across models, with very high likelihood they belong to a class on its own. And there's sort of a formal way of doing that. So I do the ensemble. I can just show you a quick visualization of that. Here's an actual example of the same input data run through a few different models, and I look for clusters that survive. There's a supercluster that survived across 3 embeddings, a number of clusters that survive. So those that survive across multiple embeddings, I take them out. There's an algorithm by which I can do this. And then when I get the final superclusters, I can then say, now I take one representative sample from each supercluster, hand it to a human, and say, give me some labels, semantic label for each of these. That gives me the fully labeled data set. So initial results are pretty encouraging, show that if you actually use an ensemble of models, you get 5 to 30% improvement in predicting labels than if you use any one model, which is the standard approach that people look at to start with. So that's encouraging. So again, you've got a bunch of unstructured data, unlabeled data, a few labels. You try to discover structure in the unlabeled data by borrowing intelligence from pre-built models and associate with your labels. So quite exciting. We hope to have some results for formal publications soon. So that was all the computational side. Now we'll get the human into the loop for the next couple of techniques. Any questions, by the way? I need to keep ranting. Stop for a minute. Okay, in that case, we'll move on. In this next family of techniques, we are looking at ways to bring human into the loop in the data labeling process through augmented reality. So my team member, Matthew Schrieg, is a principal on this, and he loves Andy Warhol, so he had to make an acronym that fit Warhol. So the technology is what we're calling wearable AR holographic object labeler. Okay, so the task is object detection. So for object detection, you need to you need to build a data set that has images and object boundaries around them. Again, you give a standard object detector 1 million images with bounding boxes, it learns how to predict bounding boxes when you give it new images. That's object detection, whatever the object may be, right? So this is of interest to us. And the way this is done right now, because you can imagine creating accurate bounding boxes around complex objects is very time consuming. You could crowdsource it, but quality of labels becomes questionable, and there's some active research in how you manage that. So how are people dealing with this problem? Well, people are creative, right? So there are a number of different ways people are looking to accelerate bounding box annotation. One approach is to do this sort of semi-automatic. There's a couple of approaches where you can you manually label 1 or 2 frames, and it uses tracking to propagate the labels in a video. This is particularly relevant for video tracking, right? But what we have seen is, these tools all make some assumptions about motion and about changes from one frame to another, and if the actual behavior in the videos violates that, then it doesn't work very well. But it's a pretty good idea. That is, if you have a video, I'll annotate every 100th frame and let the tracking sort of annotate the rest of it. But it doesn't always work. So our approach here is to use augmented reality. So we use a device like the HoloLens is the one that we use, but we could use any AR device. The HoloLens comes with a camera, and it comes with a 3D sensor. So when you look around, it builds a 3D representation of your scene. Typically use it for indoor settings. It builds a 3D mesh. Now, the basic idea is that we wear the headset, and through a combination of gesture and voice, we can, first of all, the AR system builds a 3D mesh, and then we can drop virtual markers into the scene. So in this particular case, we wanted to build an object detector for office devices like printers, right? So you wear the device and you walk around, and through your finger, you simply attach points to the printer. And because it's building a 3D mesh, it actually attaches the points in 3D space. So when you walk around, the points persist on the object. Once you've defined the anchor points, you put it into record mode, and it walks around and collects lots and lots of frames with 3D markers, but then projected onto 2D to give you 2D bounding boxes. So you've got, after one annotation, you've got a whole bunch of bounding boxes from different poses. So one of the big value here is that you get a lot of pose-rich annotation. This is an example where after doing one set of 3D annotations, you can walk around, and no matter where you walk from, you've got the projection into 2D, and you've got the annotation essentially coming for free. So let's see if this works. I'll just play this demo of object detection labeling. I think it's a little bit jumpy because it was actually taken when Matthew was actually walking around actually doing this. So initially we have to label, in which case you pick markers from a palette and you go around. You wanted to annotate a chair if you're doing chair detection. So you walk around with a combination of gaze and gesture and start marking points on your chair. And see if I can push this a little further. As you walk around, you can see that the objects, the markers just stay on the chair, right, as you walk around. Right, and then, I'm just going to accelerate this a little bit. And then during capture, now it's in recording mode. It's capturing every scene. Notice you can attach different colors to different parts. We also wanted to do object part detector, not just object detector. Well, you can attach different colors to the different parts and just walk around. And because of the fact you've got 3D reasoning about the scene, you're able to get 2D annotations essentially for free. So stop that. So that's kind of the idea here. It turns out, so from this technology, we built a few data sets that we've had available for public access. Indoor items, kitchen items, office, let me get back into office equipment, stuffed animals. You wanted to look at some non-machine sorts of objects, and we built a data set that we've made available to the public for use. So one of the things that's exciting about this is that it turns out, so first of all, how would we use this? Well, you get bounding boxes, you train a computer vision algorithm, and then it's able to then predict bounding boxes. Again, for our application, we wanted to not only identify the whole object, but also parts of the object. Okay, so the AR labeler gives us a practical way of annotating data. Now, we did a comparison because there's, again, different ways of doing annotation. How does our AR labeler compare with just brain dead manual labeling, which is taking every image and putting a bounding box around it, versus video labeling, which I mentioned was, you label every end frames and let the video tracker take over, versus AR labeler. Interesting, if you compare each of these approaches with, so we did this experiment where we knew the absolute ground truth labels, and we compared these three techniques: human labeling, manual labeling, versus video, versus ours, against the ground truth. IOU is a measure of overlap between our bounding box and the truth, and higher is better. It's a number between 0 and 1. Turns out even humans don't completely agree. There's a disagreement that gives you only 80% overlap between one human and another. Video labeling is very poor. AR labeler, not as accurate as manual, but pretty close. But if you look at the total time taken for the annotation, right, so that we think that's a really nice trade-off. Pretty good accuracy, very, very fast way of annotating data. And it also turns out that not only is it fast, we can use our technique to enhance state-of-the-art object detection. So let's say you want to build a chair detector, and there are lots of chair detectors out there, believe it or not, for different retail applications. So we took a standard detector trained on the Pascal chair data set, and if we then we went within Park and annotated a bunch of chairs using our AR labeler from all kinds of different poses, and then add that to the training set and run a standard detector on our augmented set from our system, you get a 10% improvement from 40 to 50%, which is huge in the computer vision community, right? So, and one of the reasons for that is that, images on the web often have some bias to them. They're all taken a certain way. They're frontal, there's nice lighting. There's certain biases for if you look at images uploaded on the web. We try to overcome that bias. You can walk around a chair, you can look under it, you can get all kinds of unusual poses, and that gives you a much more robust way of detecting chairs, right? So it helps us improve. So that's pretty exciting. More specifically for us, we wanted to build, this was a Xerox-sponsored application. So we built actually a technology that allows users, that assists users with operating with specialized equipment like printers and copiers. So the vision is that you either wear a device like the HoloLens, or you take a tablet in front of a printer or copier, and let's say you want to change the diffuser roll or change the paper tray or something that's complex. You can use this device to detect and give you a guidance. If you think about if you run into a paper jam or you have some problem with your machine, what do you do today, right? You look up the web, you look up a YouTube clip to see a DIY YouTube clip. But the problem is that YouTube clip has no idea of your specific problem, and if you're partway through trying to fix the problem, YouTube's not going to know where you're at, right? You have a static view of how somebody else fixed that problem, but you don't have the interaction. Our technology will actually watch you and see if you're doing it right and give you guidance based on what you're doing, because there's computer vision. It's looking for objects, it's looking for parts and things like that. So a little demo here of this is actually looking through the lens of HoloLens with our technology. It's giving you a state of, giving you a state of different document feeders open. It's giving you sort of the state of the device, and it's giving you a digital twin to show you as soon as you open the real printer, the digital twin also opens. So it's actually tracking what you're doing, and that way it can give you real-time guidance based on where you are. If there's a 5-step process, it'll wait. If you're in step 2, it'll wait till you're done with step 2 before it starts with step. It knows whether you've done step 2 right before it goes to step 3. This is interactive sort of feedback. So that's where the object labeling came in. So that's something we're excited about and looking for sort of different applications for that. And then in the last few minutes, I'll touch our last bubble. So far, quick recap. We've looked at ways to bring intelligence into networks through regularizers and priors. We've looked at ways to auto-annotate data which is not annotated. And then we've brought a human into the loop to do annotation using AR. And finally, we're going to bring again the human into the loop to improve the quality of capture, right? And the particular application that demonstrates this particular smart data capture came out of a project again with Procter & Gamble. So Procter & Gamble, as I think many of you may know, builds, amongst other things, develops beauty products. There's the Olay line of business that makes and sells different types of facial cleansers and facial beauty products. So they collaborated with us to come up with a technology to help them with this. So to understand that problem, I'm going to jump into P&G land for a couple of minutes and to give you an idea of what the problem is. So this is Procter & Gamble. They have, for example, an Olay beauty counter at a store. And they have lots and lots of products. So there's no lack of products they have on the market. But they have a big problem in that there's a lot of confusion. Right, the statistics from P&G. By the way, this is from P&G marketing. That's why their slides look so much nicer than mine. But there's a real statistic that says that large percentage of women are overwhelmed when they go to the beauty aisle. They don't know what they're looking for, right? They don't know if the product's right for them, and only 14% of them, 14% of women say they don't know what their specific what their needs even are, right? Let alone going and looking for the right product. So there's a maze, there's a myriad of products, there's a lot of confusion. How do we deal with this? So what they did to respond to this problem is come up with a platform called Olay Skin Advisor. It comes with a mobile app. If you're interested, you can download it. It's available. It's a mobile platform which does the following. The idea is that they wanted to leverage technology that everybody carries in their pocket, namely your smartphone and its camera. The idea is that you take a picture of yourself, selfie, and upload it to the web where it does some analysis of the skin. It asks you some questions about your demographic, your lifestyle, etc. And then between your self-questionnaire and the skin analysis, it provides you recommendations for products, very pointed recommendations. So the whole point is that you cut through the clutter. You don't have to go to a confusing beauty aisle, right? You take your phone out of your pocket, you go through this process, and the idea is to give you quality, personalized skincare based on your skin condition. And not only that, being able to do that on a continuous basis, right? Since you can do this sort of thing, you can capture images every day and track your skin condition over time, look at the efficacy of a particular product over time. So that's the idea here. So one of the first things we ran into in starting to develop this technology is you look at the quality of selfies people capture. You think, wow, it's pretty shocking, right? Most prevalent problem, the lighting is very poor. People take blurry pictures. They're taking it from an angle. So the problem is garbage in, garbage out. This is purposely blurred by them just because for identity purposes, but images can be pretty bad, right? So what do you do? And this led to another problem they had is, customer credibility was starting to wane. Of course, they did it as an internal rollout. And people saying, you're taking this crappy selfie and telling me about this about myself? I'm not sure I believe it. Okay, so problem, how do we deal with it? The problem is we don't have control on the quality of the capture. We're not monitoring the quality of capture. Can we filter out the bad selfies, right? Now, the kinds of issues that affect skin analysis, the ultimate task is to analyze your skin and give you some useful information about your skin. The classical elements that adversely affect that analysis are poor lighting, uneven lighting, right? If I have lighting like this, then how am I going to disentangle lighting from some pigmentation issue, right? That's hard to do. Expression is not good. Ideally you want neutral expression when you capture faces for skincare, because otherwise you can introduce artificial structure and wrinkles, and that gives you a wrong signal. Are your wrinkles due to poor skin or because you were smiling? So you don't want to smile. Obviously you don't want anything in front of your face to hide you. But these are real pictures people take when they use the app, right? So not very workable. Can we detect these conditions? It turns out that's what we did. So if you sort of zoom in on what Olay Skin Advisor is, you upload an image, and this is technology that we built for Procter & Gamble. It's under the hood from Park, from my team. We want to do skin analysis, but before we do skin analysis, we incorporate a technology called Smart Selfie that filters out bad images. Okay, so let's see a little bit about how that works. So I'll just do that through demos. Basically, we have a series of filters. So I should first mention that in the product that's out there in the market now, everything is done on the cloud. You take a picture of yourself, goes off to the cloud and crunches and sees whether the image is good enough. If it's good enough, it'll do the analysis and tell you your skin is great or not, give you a score. But if the image isn't good, it'll come back and say, you didn't take there wasn't enough light. Can you please retake your image under better lighting? Or can you please stop frowning? Or can you please take your hand out of in front of you? Whatever. It could be a nice polite message, but it's going to give you a message a few seconds later. The problem is, when this happens a few times, consumers are not going to be very patient about this, right? So Ideally, you want the feedback to happen on the phone in real time as you're getting ready to take the picture. As you're standing in front of the phone, you want it to be able to guide you so that you can just get the picture right in the first place. So in our latest instantiation, we built the computer vision into the phone to tell if you're taking a good picture in the first place or not. So rather than going through all the algorithms, I'll just go through some of these effects, and I'm happy to talk about the details of any of these approaches. So the first one is how far you are from the camera. You don't want to be too far or too close. If you're too close, you could miss part of the face. If you're too far, there isn't enough resolution. So we have a simple detector to look at the size of the face relative to the size of the image. The message on top, it tells you just whether you're too. If there's no message, the image is okay. If you're too close, it'll warn you. If you're too far, it'll warn you. And by the way, this is just our research app. So these are messages that are written by Park researchers. By the time PhD takes, they're going to produce some nice, very nice user interface with nice messages. But this is just to give you a sense for the fact that we're doing real-time monitoring on preview frames on an iPhone, right? So this one is for pose. We want frontal pose. If you don't have the right pose, you hide part of the face. So this just shows that this is giving you an instruction, detecting in real time whether you're looking straight or not. This is just for demonstration purposes, but it's very fast. It's a pretty accurate image. You move your face very quickly. It tracks in real time. This particular filter is for motion. If there's blur or shake, it's going to warn you by applying some blur analysis on the image. One of the most important factors is lighting. So we have to build a fairly sophisticated lighting detection engine to tell whether you have enough light or not. I'll tell you a very interesting challenge in this problem is dealing with diverse ethnicities. So you can imagine dark-skinned people. If you just naively take this experiment and say, I'm going to look for a certain brightness in the skin. If you have a dark-skinned person, and if the app is always complaining there isn't enough light on you, this is not a happy customer, right? Yeah. So we have to do a lot of training to deal with ethnic bias, and at Park we don't have a lot of dark-skinned people, and in fact this is a big issue in computer vision. Data bias, ethnicity bias is sort of pervading itself as a concern into all kinds of computer vision problems, and certainly this is a classic one, right? But anyway, we did, to the best of our ability, balance diversity. So here's an example where it's right now complaining low light, and as Jayshree, our developer, changes lighting, it's going to sort of say it's uneven or dark, and so we're using, here what we're doing is we're looking at histograms of luminance across the range of the face, fitting that to sport vector machine to classify different states of lighting. Again, I'm happy to talk about algorithms, time permitting. Here's another example. No message means good light, and I think she'll turn on the lamp and it'll say bright. So again, you want to just be able to take the picture right the first time and have to go through this loop multiple times, right? A couple of other filters. These were more complex. These required deep learning algorithms on the phone. So we figured out how to do that running in real time. The first one is expression. And I think this one is just going to basically complain if Jayshree starts to show expression. We can also tell what kind of expression it is, but see her make some funny faces, I think. Yeah. So it turns out that expression detection is actually quite challenging. You can't do that using simple image processing techniques. So we have to run a deep pipeline to do this. And then this one is occlusion, which is also somewhat complex. Right, so, and both these techniques required sort of deep learning. So it was very challenging to build sort of deep learning on the phone to work in real time, but something we were able to do. And so now that we have a filter to give us only good data, we are ready to solve the second problem, which is skin analysis. Now here, there's a whole bunch of skin analysis techniques that we're developing with Procter & Gamble. I'll give you an example of one we're looking at, which is called perceived skin age. So it turns out that there's a measure for how young or old you look just from your skin, which is a proxy for the quality of skin, right? Everyone wants to look young, and the reason for that is because you have a certain elasticity in the skin, and that's also a sign of good skin health. An example, this picture is a very interesting one, came in New England Journal of Medicine some time back. This man was driving a delivery truck for 28 years with the sun exposed to only one side. So you can see how photoaging has sort of manifested itself only on his left side of his face, right? So skin age is not just a result of chronological age, it's also a function of ambient conditions and how well you take care of your skin. So P&G wanted us to build algorithms to predict the perceived age of your skin based on your mobile selfie upload. So we built a deep vision pipeline. This was published in Machine Vision and Applications. I can discuss the details with anyone interested to predict skin age. The important thing is, so we have a task, right? The task is, I have a face, I need to predict what the skin age is. What we want to do is measure what the impact of smart selfie was on that task. The fact that we had a bunch of filters to give us only good data, what impact did that have on our final task? So this curve kind of shows that nicely. So what this is this is showing the accuracy of skin age prediction as a cumulative error histogram. So the x-axis is error in prediction, and the y-axis is the cumulative probability. If my model was perfect, it'll give me 0 error 100% of the time. So that corner is where I want to be. Okay? So the closer you are to that corner, the better the model is performing. The blue curve shows what we get. It's an ROC curve we get by varying certain parameters without smart selfie. And these other bunch of curves is from using smart selfie with different strictness settings, how picky you want to be about how good images need to be. You can see a big improvement, right? So if you want to guarantee that I'm within 10 years of error in age, which is already a lot, turns out without smart selfie, the way people take pictures, only 50% of the pictures are going to be good enough, are going to be, only 50% of the cases are you able to predict error within 10 years. Whereas if you use some sort of image quality check, 90% of the time I'm under 10 years, right? So this is a big boost. So if you can control the capture, if you can co-optimize capture with the analysis, that's always a very good thing. Okay, to wrap up, I hope I've convinced you that it is possible to get big insights from small data if you do it the right way. Domain knowledge can really help, right? If you can incorporate knowledge into your network. And of course, the challenge there is to take some real-world knowledge and articulate it in terms of some mathematical differentiable smooth function. But if you can, that can help us cope with data constraints. There is a lot of useful information, a lot of structure in unlabeled data. So if we can use it, that's always a good thing. And by the way, I should say, sort of the next generation of computer vision, many leaders in the field are placing big bets on unsupervised learning and learning with very, very few labels and discovering structure in unlabeled data. It's really sort of next frontier of computer vision and machine learning. Human in the loop can enhance the quality of data, as we saw in Smart Selfie, and can sort of also accelerate labeling if you build it the right way. And this last message is, again, we talked about co-optimizing image capture with the analysis. To me, the sort of the broader statement is if you can adopt a systems approach to computer vision, right? So computer vision is not just a bunch of data and labels and machine learning and prediction. It's the whole system. You've got the scene, you've got the camera, you've got lighting, you've got optics, and a camera placement, camera geometry, how that affects the data, and what's the final analytics. So often when we approach problems, we try to look at the big picture and see what elements in that big picture we can actually touch and affect and co-optimize instead of going tunnel vision, no pun intended, on just the deep learning, right? So with that, thank you. Happy to take any questions. Yeah.
Yeah.
Yes.
I have a couple of questions. For the first one, the human in loop, that one, and when the user click, somehow using the AR glasses, and but the image look into the human eyes is still a 2D image. How does system detect what is the depth for that image?
Oh, it's good. So there's depth sensors. I'm showing you just a 2D image, but the HoloLens has depth sensors. And the first thing it does when you put it into a first programming mode, it creates a 3D mesh of the whole scene. And so when I'm looking in front of me, there's a 3D mesh. And when I'm pointing at any given location, it projects to the closest point and places a point on there. Yeah. So that's the way it disambiguates.
And the second question is for for using multiple ones, you use multiple systems, multiple neural networks, and use the same data and try to do the clustering
Right.
for the features.
Yep.
And have you thought about something like using different data and see using the same system, the neural network or different neural network, and see whether other kind of label, other kind of data, and complete something like similar data distribution and use other data to compensate for this one.
Other data. That's an interesting idea. Yeah, basically in this study we had lots and lots of unlabeled data. But there is a variant, which I didn't talk about here, which is that if you have some data from another source which is labeled, you could use that in here as well as a side information. We have to flesh that out a bit. Is that
Yes, okay.
That's your suggestion? Can you take other data that's labeled and use it as well?
Yeah, I want to see whether the distribution for even not labeled, if by clustering their distribution is similar to
Another data
Yeah.
distribution. Okay. But if that other data is also unlabeled, what's your suggestion to?
Use I would say that should be labeled data.
It should be
Yeah.
labeled. Okay. If it's labeled, it can give you hints. Yes. And the labels need to be similar to the task. Yeah, it's a good idea. We have another sort of variant where you have some labeled data in a related task and do some cluster analysis against this, this data set that gives you a better way more robust way of generating labels.
And how do you select the neural network here? You want to select a few, right?
Yeah, that's a good question. So it started out being somewhat heuristic. If I'm doing image classifier for a certain class of images, I go and look for models that are on similar classes, just sort of manually. But we're coming up with more automated ways. One way is that you know what your task is. I mean, you've got unlabeled data, you know what your task is. Let's say you want to build a classifier, and you know what your class labels are, right, depending on the problem of interest. You can throw those labels against the labels of different models to see where there's maximum label overlap, and pick the models that are most closely related to your task. That's one way to do it. Another way to do it is to go the data route, look at embeddings, and look for overlap between your data. And if you have access to the data that was used to train these models, model to model N, you could do some data overlap analysis as well to select the model. Yeah. Yeah.
For a skin color bias issue, a possible solution would be to lighten the picture, but not show it in front of a person, then it'd be easier for a program to detect the outline.
Lighten the picture, but
Well, showing it.
well, sure, you can apply some pre-processing. Yeah. You just want to make sure that the features of interest are there, right? Fundamentally, if you have a dark face, let's say I have a way to, I can detect the face and landmarks and things. If I have a dark face, how do I disentangle whether it's skin color or poor lighting? And even if you look at the overall scene, that can sometimes be hard to do, right? I would suggest to Procter & Gamble, can you, in your self-questionnaire, can you ask about ethnicity?
I was wondering.
Oh.
Yeah.
That's a tough one.
Right.
But it turns out there are deep networks that can be trained to predict your ethnicity.
Right.
And interestingly, those deep networks don't use color as human might think. They actually use other structure too.
Oh,
They discover a structure between, say, nose shape and ear shape and ethnicity, and are automatically, because deep networks, they learn all these correlations and then learn to, if you give it enough examples, it learns that it's not just color, so that even if you had an Asian person or a Chinese person under low light, it'll learn that, because you're giving it the label that the person is Chinese and not, say, African American, it'll then say, oh, I can't depend only on color, I must also look for a different face structure. And it learns to discover that pattern, right? That's the beauty of enough examples. So I guess we could run a ethnicity detector first. Yet it all has to run on phone in real time, but we can figure that one out.
All right.
All right.
Let's thank our speaker one final time.
Okay, so
Have any questions?